Hello everyone, welcome to our differential equation class. In this video we continue our applications of the linearization analysis. In this case we are going to focus on the predator-prey system, which is a nonlinear system of 2x2 differential equations. We are going to study in detail the case where the prey has infinite food resources, and then we are going to compare these solutions with the solutions in the case that the prey has finite food resources. So that's the plan for today. Let's start introducing the predator-prey system. There are two main types of equations for the predator-prey system. The first type of equation is called the infinite food case, and the second type is called the finite food case. Let's focus on the infinite food case. The predator-prey equations in this case is the following. We have two unknown functions, x1 and x2, which are function of time. x1 represents the population of one species that we call the predator species, for example, hawks or foxes. And x2, as function of time, represent the population of the prey species, for example, rabbits. So our predator species, hawks, for example, hunt rabbits. And here is the equations for this system, recall in the case of infinite food resources. So let's try to understand what these equations are telling us. To do that, it's a good idea to suppose that we don't have one of the species. So let's start with the predator. Suppose we don't have predators. Suppose x1 is 0. So we don't have any predators. Then in the first equation we have x1 in all terms. So the first equation disappears, is 0 in all terms. And in the second equation x1 appears here, so this is also 0. So we end up with only this equation for x2, which is the population of the prey, of the rabbits. And this equation is the equation of the exponential growth equation, because pretty soon we are going to say that the coefficient h2 that appears in that equation is positive. So this is what we mean when we say that the predator-prey system has infinite food resources for the prey. The equation that describes the prey alone is the exponential growth equation, which, as we know, this equation has a solution that grows, if this is x2, grows exponentially with time. What happens with this system when the prey is 0? If we don't have any prey, then now the second equation contains x2, x2, and x2, so the second equation disappears completely, and in the first equation, the second term that has x2 disappears. And now look what we have here. What we have here is the exponential decay equation for the predator. The reason for that is that we are assuming in this system that the predator, the only food resources for the predator is the prey. So if we don't have prey, the predator dies, and dies pretty fast. So the solution to that equation, the exponential decay equation for x1, is exponential decay. So that's what happens with the predator when it's alone. And again, we are assuming in this case a1 is a positive coefficient. So the negative sign makes the decay. So this is what happens, how we interpret the first two terms in the two equations. And then what about the second term? The second term is describes the interaction between the two species. For example, when a predator meets a prey, and this product is different from 0, then this is good news, so positive contribution to the growth rate of the predator. The predator has food, and it's bad news. All these coefficients b1 and b2 are positive for the prey. There is one rabbit less. So this is essentially the predator-prey system in the case that the prey has infinite food resources. a few remarks that we mentioned already. Let's put it in writing. The coefficient A1 is positive, so this negative sign has a meaning. And A1 is the death rate of the predators. When you can see that when there is no prey, this is what is going to model the predator population in that case. A2 is the birth rate of the prey. We have a positive sign here. And the coefficients B1 and B2 are the interaction coefficients, and each coefficients they are describing how each species affect the other. For example, the coefficient, if we have a big predator, for example, foxes or a big animal is a predator, then killing one little rabbit is going to be a positive contribution to the predator, but because the animal is so big, this coefficient may be very small. And maybe this coefficient is larger in the interaction coefficient. So the magnitude of this coefficient is related to how is the interaction between the predator and the prey. This is the case of infinite food resources. We are also going to study in this video the case where the prey has finite food resources. So what we are going to do is we are going to modify this equation. This equation is going to be the same. By the way, this equation is going to be the same, and this equation is going to be modified. But before we go into that, let's clarify something. Suppose I give you a system of equations like this. We already said x1 is the predator, and we described the equation, but maybe you write the equation in a different way and you say x2 is the predator instead of x1. So how you recognize just from the equation which variable represents the predator and which one represents the prey? And what you need to do is what we already did: kill one of the variables. So for example, kill x2. So x2 equals 0, and see what remains for x1. And you see for the x1 we have, as we mentioned already, the exponential decay equation. That means x1 is the variable that represents the predator. So that's why x1 is the predator. So now we obtain the information just from the equation. And if you kill the variable x1 and you see what you are left with, you are left with the exponential growth equation. So that means x2 is the prey. It grows when it's alone. So the predator variable goes to 0 when it's alone, and the prey variable grows to infinity when it's left alone. So that's how you identify, given the equations. If nobody tells you this information, just from the equation you can see, you can read which variable is the predator and which variable is the prey. Okay, now we can move on. Suppose we have finite food resources. What changes? Well, what is going to change is this equation, the equation for the prey. Instead of having this equation, which is the equation of the exponential growth, we are going to introduce the logistic equation for x2 plus the interaction. That's the only modification, and here is what we get. You see, the first equation is exactly the same in both cases, because that's the equation for the predator, the rate of change of the predator. And now the equation for the prey contains this term. This term is exactly the same as before. And now what we change is this part of the equation, which now is the logistic equation for the prey. We have this new term. So there is one new term, which is this term. Recall, it has x2 squared because we are multiplying by x2 here. Is proportional to negative x2 squared. So this is the logistic equation. So maybe it's a good idea to, if we consider only these two terms and nothing else in the equation, this is the logistic part of the equation. Logistic part. We have studied the logistic equation in a previous video. So the coefficients here in this equation, well, they have all the same names as, oops, let's do it like this, as in here. Plus, there is one new coefficient, which we know from the logistic equation. This is called the carrying capacity. And that coefficient describes how many individuals can be sustained, individuals in the prey population, can be sustained by the finite food resources available. So these are the two equations we are interested in to study. The competing species with finite and infinite food resources. Let's go to the main part of our video, which is to sketch an approximate phase portrait of the solutions to the predator-prey system in the case that the prey has infinite food resources. And instead of working with the most general predator-prey system with infinite food resources, we are going to give some arbitrary values to the coefficients, and we are going to work with this system. We have called the variable that describes the predator, we call it H. You should keep in mind hogs, the population of hogs, and R for the population of rabbits. So it's easier to identify which variable we are talking about. So let's solve this problem. Well, we are not going to solve it. What we are going to do is we are going to use the linearization analysis we have introduced in the previous video to sketch a qualitative phase portrait of the solutions of this system. So let's introduce the field associated to the equation. So introduce the field, and we are going to call the field f, and f is going to be function of x, and x here is going to be hogs and rabbits. So let's use it. The variable hog is going to be the variable in the horizontal axis on the pictures, and rabbits in the vertical axis. And what is the field then? Well, the field is going to be something more or less like this. The first equation on the first component of the field, so minus 4h plus 7h times r, and then the other equation is 5r minus 3hr. And that is what we are going to call, if we need it, the first component is going to be f1, the second component is going to be f2. Or we can call it f, h, and r, but it's better f1 and f2. Okay, where do we start with our linearization analysis? We start with the equilibrium solutions, or critical point. Equilibrium solutions. And recall they are also called critical points. Okay, and how do we find these critical points? Well, they are the solutions, they are the points where the field vanishes. So let's put it here a little bit smaller. These are the points where the field vanishes. So we have two equations. The first equation is going to be, and in order, we are going to rewrite is going to be the first component equals 0. We are going to pull common factor h, and then we are going to write it as h that multiplies -4 plus 7r, that is equal 0. And then in the other equation we pull r common factor, so we have the rabbits multiplying 5, let's make a better 5 minus 3h hogs equals 0. Okay, what do we get from here? Well, here is one solution, h equals 0 and r equals 0. H equals 0 satisfies the first equation, and r equals 0 satisfies the second equation. So we have h equals 0 and r equals 0. Okay, any other equation, any other possibility? What about if we put h equals 0 and then we try to find an r different from 0, so solution of this equation. Well, that is not possible, because if h is 0, then this h here is 0, so it's not there, and then the equation is 5r equals 0, so r has to be 0. So this is the only case, this is the only solution when h is 0, and when r is 0, we satisfy the second equation, then we go here, this term is not there, and the equation is negative 4h equals 0, so h has to be 0. So when either of the variables is 0, the other has to be 0. So the only other possibility to satisfy these two equations is to choose h such that this is 0, and to choose r such that this is 0. So h is going to be 5/3. So let's write it down. Or h is 5/3, and r is whatever need to be 4/7. And that's it. These are all the critical points we have for this system. So we can write them in the usual way, in the way that, let's put it here, we have x0, which is the point 0, 0, and then we have one more critical point, and that's it, which is the r is, and we are putting h first, so h is 5/3. Then the rabbits, and the rabbits are 4/7. And that's it. Two critical points. So if we do the picture, so this is how they look like. The numerical values are, this is close to 1.6, more or less. This is close to 0.6, so it's more or less like here, the picture, right? Like we have there. And recall that sometimes we are going to use the point notation, so HR, and sometimes we may use the vector notation, which is HR, for the same information, the components HR. Okay. What next? Once we have that, the next thing to do is to compute the derivative matrix. So derivative matrix. Okay. What is the derivative matrix? Recall in the notation when the field, we write it as F1 and F2. So the derivative matrix, which is a function of the point, is going to be a matrix 2 by 2, where in the first row we are going to have F1 twice. In the second row we are going to have F2. And in the first column, we are going to have derivatives with respect to the first variable, which is h, on both hogs. And then in the second column, derivative with respect to the second variable, which are the rabbits. So this is how we remember in which order we have to put the derivatives and the components. Here in the first component, in the first column, we have derivative with respect to h. In the second column, here we have derivative with respect to r. In the first row, we put f1. In the second row, we put f2. Very easy. Okay, let's do the calculation. So let's put the derivative matrix here. And what do we need to do? We need to do the derivative with respect to h of f1. f1 is that quantity, so negative 4h plus 7hr, and the same here, but derivative with respect to r of the same quantity, negative 4h plus 7hr. And now in the second component, we have the derivative with respect to h, but of the second component, which is up here, 5r minus 3. Okay, 5r minus 3hr. And here is the derivative with respect to r of the same function, 5r minus 3hr. Okay, that is the calculation we need to do to get the derivative matrix, and here is the result. The derivative matrix is a function that is going to be negative 4 plus 7r. Then this component here is derivative with respect to r, so it's going to be 7h. Down here we are going to have negative 3r, and then over here we are going to have 5 minus 3h, and that's it. This is our derivative matrix. I just did the partial derivatives indicated in the previous line. So now what we need to do is we need to evaluate this derivative matrix at the critical points. One critical point is the 0, 0. So that gives us one derivative matrix at the point 0, 0, which is very easy, is negative 4, 0, 0, positive 5. The other is the derivative matrix at the point x1, which, if we recall, where is the point x1? Is there 5/3, so it's right here. 5/3, oops, 5/3, and then 4/7. Okay, that is gonna be a little bit more work. The derivative matrix at that point is then, well, let's see. Let's go slow. We are going to have negative 4 and then plus 7 multiplied by r. Recall, this is our r. So r is going to be 4/7, and then we have 7 multiplied by h, which is 5/3. Then we have negative 3 multiplied by r. By r is 4/7, and then we have a positive 5 minus 3 multiplied by h. H is the first term, so it's going to be 5/3. So you see what happens. The diagonal elements vanish. So this so what we can see is we cancel these two and then we get 0. We cancel these two and we get 0. And then the derivative matrix is nothing more than, let's put it here, the derivative matrix. Let's put it at this point, at 5/3, 4/7. It's going to be 0. Then we are going to have 35/3, and then we are going to have 12, negative 12/7, and 0 again. Alright, these are our two derivative matrices. That's one, that's the other. What do we do now? Well, we need to solve linear systems, so the linearizations. So let's do it over here. Linearizations. One for each critical point. So for the point x1 or x0, which is 0, 0, we need to solve the linear system u prime equal, well, this is a very simple matrix, negative 4, 0, 0, 5 times u. So how we do it? We compute the eigenvalues. And then we compute the eigenvectors. for that system, but we don't need to compute anything. Everything is given right there. The eigenvalues, we have a positive eigenvalue lambda plus, which is 5. Then we have a negative eigenvalue lambda minus, which is negative 4. And then the corresponding eigenvectors is v plus is going to be 0, 1. So it's a vertical pointing up eigenvector, and then v minus is going to be 1, 0. And you see from here that for this critical point, the solution u equal 0 is going to be a saddle node. And if we do the picture, I already have the picture done here to save a little bit of time. So we have the eigenvector v plus in the direction of the positive eigenvalue is 0 horizontal, 1 up. So I don't know why I drew it in this way. It should be that way, but it doesn't change anything. It's just a different eigenvector. So let's put it here. This is the v plus, and the v minus, that's correct. This is the v minus, and you see it's a saddle with this geometry here. Okay, for the linearization. Good. And this behavior of solutions of the linearization will translate into the solution of the nonlinear system near this critical point, because our main result of between linearizations and nonlinear systems. So now let's move on to the next point, the last point actually, x1. Let's put it here, x1, which is that point 5/3, 4th, 7th. And recall, now we need to solve the linear system u prime equal, and now we have a matrix, that is that matrix over there, which is 0. Then we had 35/3. Then we have here negative 12/7 and 0 again. It looks complicated, but it's not that difficult to find the eigenvalues and eigenvectors. Let's copy that so we don't need to write it all over again. The eigenvalues in this case happen to be lambda plus is going to be, if you do the calculation, they are going to be, this is the system we want to study. U prime equal the matrix times u. And this matrix is going to have complex eigenvalues. Complex. Eigenpairs. Both are going to be complex. And if you do the calculation, it's not difficult to see that you're going to get the square root of 20 times I, and the other eigenvalues, the negative, is going to be minus square root of 20 I. And what are the eigenvectors? Well, the eigenvectors are going to be v plus, the corresponding to lambda plus, is going to be 7/3 in the first component. The second component is going to be 4/5 square root multiplied by I. And we know that if this is the eigenvector for lambda plus, the eigenvector for lambda minus is the complex conjugate. So it's going to be 7/3 and then minus the square root of 4/5 multiplied by I. And recall, if we want to do the graph of the solutions, let's make more space between the two cases so it's not all cramped up. Maybe here. And recall, if we want to draw the phase portrait, it's important to write the vector v plus in terms of real and imaginary parts, and here they are. The vector v plus is actually the vector 7 third 0 plus the vector 0 and then square root of 4/5 multiplied by I, well, I is going to be outside, multiplied by I. And if we do the calculation in a calculator, so this is more or less is a 2.33 something 0, and the other is 0, so this is 1, and the other is just to have an idea the length of the vectors. One is has length 2 in the horizontal direction, and the other is 0.89, so 0.9 probably times I. So this vector is much longer than, is twice, at least twice as long as the other vector, and these vectors, recall, have names. This is usually called the vector A, and this is usually called the vector B in previous videos. With that information, we realize that the solution u equals 0 is actually a center, and it looks more or less like this. You see the vector A is more than twice as long as the vector B. The vector A is horizontal and the vector B is vertical up. So then you plot the vectors negative B here and the vector negative A. The direction of rotation, recall, is always in the direction A to negative B. So we are moving, in this case, clockwise. So all that is from previous video. So I'm not repeating what we did in previous video. So this is the behavior of the linearization. Now we have a problem, because the main result we are using to find the behavior of the solution of the nonlinear system is the Hartman-Grobman theorem, but unfortunately the Hartman-Grobman theorem does not apply to centers. So in this case, this theorem does not imply that the linearization and the nonlinear system have the same behavior. It does not. So we don't know. Maybe they have the same behavior, maybe not. What we can conclude right now is, up to now, using only the Hartman-Grobman theorem, is that the behavior of the solution of the nonlinear system near the equilibrium solution x0 equals 0, yeah, the solution of the nonlinear system behaves like a saddle around here. But what happens here, we don't know. Is a center? Maybe. Maybe it's a spiral, maybe it's a node. We don't know. At this point, we don't know. We need more information to determine what is the behavior of the solution here. Hartman-Grobman theorem is not going to tell us what is happening here. So what we can do? There are many ways to obtain more information about the nonlinear solution near this critical point. Maybe the simplest and the one we have seen in our videos before is to draw direction fields. And if you draw the direction fields near this critical point, you're going to see that actually the behavior of the solution here is actually like a center. So with that information, extra information coming from the direction field, we conclude this, which is more or less so the phase portrait of the solution of the nonlinear system near the critical point for the nonlinear system is also a center. So there is a center here, there is a saddle node, and how we do the graph of the solutions in between. Well, this is a guess. Again, we need more information to extrapolate the behavior of the solution here and here to the rest of the phase space. But again, with direction fields and further study, a good guess is that the behavior of the solution is going to be what we draw here. Nothing else is going on. So we have a center here, and you can draw the direction field on the axis. This is easy to do. So you get these solutions moving along the axis. You see, this is what we described before. When we are on the predator axis, the solution goes to 0 because the predator population disappears. There is no food. And on this axis, the prey axis, there are no predators, so the population goes to infinity, exponential growth. This is what we mentioned before. And what happens when the two populations are different from 0? We move along these closed curves. And this closed curve, essentially what they are saying is we move always on the same curve forever. So the population of predator, for example, if we are in this curve, the population of predator is going to be moving back and forth on this interval, and the population of prey is going to be moving back and forth on this interval forever. So the population of the prey and the predator oscillates with different amplitudes. The amplitudes are related with the shape of the curve, but there are oscillations in time. This is what the interpretation of a closed curve here. Closed curve means the population of both species oscillate in time forever. We can see that if we grab one of these curves, for example, that solution, and we put some initial condition. Let's put an initial condition here. So some population of predators, some initial population of prey. The solution curve says we are going to move in this direction. So the population of the predator is going to decrease until we reach here, and then stays more or less the same, and then the population start to move into the other direction. It start to increase until we reach here, and then the population start to going on the other direction. So the population goes in this direction, later on goes in that direction, then goes in this direction and that direction forever. So the population oscillates. So starts here, it goes down, it goes up, it goes down, it goes up as function of time. If we put time here. And this is what we try to represent in this picture. If we add time, because the population moves on this axis back and forth, this is what we obtain, an oscillation. And this is h, the population of the predator as function of time. Exactly a similar behavior we have on the population of the prey on the other axis. The population of the prey is going down, then here is going up, then stays more or less there, and then going down again. So it's going up, then it goes down, then it goes up, then it goes down, and it does it in time. So here the population goes a little bit down. So we start here, it goes a little bit down, then it goes up, goes down, goes up, goes down, goes up and down as function of time, which is more or less what we have here. So we have oscillations with different amplitudes, because this is not as if we have a circle here, both amplitudes would be the same, but it's not, so they have different amplitudes. And we can put these two functions together, and this is more or less what is happening. We have two oscillations out of phase. When one of the population is low, the other is high. When the population of the rabbits go high, the population of the predator goes down. And how we interpret that? Well, this is actually what happens in the physical world. If you have very low population of rabbits, then and you have a lot of foxes, the foxes are running out of food because you have very little rabbits. So the population of foxes goes down because they don't have food. But as soon as the population of foxes goes down, then the population of rabbits recovers and goes up. The population of foxes go down until at some point the foxes start finding more food and start feeding on the rabbits, and this is bad news for the rabbits that the population goes down. So this is essentially what happened. The shape is not exactly the same because the shape has to be done more carefully, and to do that we have an interactive graph with a computer. So let's go over that now. Okay, here we have our interactive graph. We are plotting the direction field of the predator-prey system with infinite food resources for the prey. Here is one solution curve with this initial data. Here we have we can move the initial data. Here we have foxes and rabbits. Okay, so we are moving the initial data. So let's put some initial data over there. And if we move time, this is what is happening. And notice that we are moving in the opposite direction as what we had before, and this is because the axes are on the opposite way than in the nodes. So the direction depends on which axis is the horizontal axis. Before we have the predator, recall the hawks were in the horizontal axis. Now we have the rabbits in the horizontal axis and the foxes or the hawks on the predator on the vertical axis. We could change the code to do it on the other way, but it's good to know that the direction of rotation depends on which axis you have the predator and in which axis you have the prey. The projections of the movement of the solution, you see how the green dot is moving. This is the solution as function of time. Let's go back to 0. The projections on the axis give you the population of rabbits or predator as function of time. Here is one of the populations. This is the rabbit population. This is the foxes. This is more precise now. This is the two oscillations. They are out of phase, but now it's more precise than my writing of the curves by hand. And you see that when the population of the rabbits goes to the maximum, then the population of foxes start to increase. But now, up to this point, is too much for the rabbits. You see what is going to happen as soon as we move a little bit more time. So after this time, there are too many foxes, and then the population of rabbits start to decrease because this is the level of population of foxes that is too much for the rabbits. But the foxes still have food, so they are still increasing, and the population of rabbits are decreasing now really fast until this point, and this is the minimum population of foxes that can sustain this population, the population of rabbits that can sustain this population of foxes. And now there are too many foxes, and they are hunting too much, and then let's go back, and then still too many, until we reach a level of foxes that is enough for the rabbits to recover. And this is what this curve is actually doing. And well, this is how the oscillations happen, and they are oscillations forever. So this is a more precise picture of the solutions of rabbits and foxes when you solve the equations numerically. Back to our notes. This is more or less the qualitative picture of the solution as a function of time, and here we repeat again the same picture we had before. Just as a summary, the populations of predator and prey oscillate out of phase. This is what we mean here by out of phase. They are not oscillating in exactly the same way. They are shifted one from the other, one oscillation from the other, without any decay. They oscillate forever. And this is what happens when the prey has infinite food resources. Now we end our video with a brief summary of what happens to the equation when we have finite food resources. Well, we know what happens to the equations. The equations are modified by adding an extra term that is proportional to the population of prey squared with a negative sign and some coefficient. So here we have chosen some values for the coefficients, so we have a nice picture at the end. But you see, this is the equation for the predator as before, because when we kill the interaction, the predator dies, and when we kill the interaction, this population is described by the logistic equation, which this is what we mean by finite food resources. So this is the question for the prey, this is the question for the predator. If we do the linearization and all the calculations we did in the previous case, we repeat those calculations for this system, we are going to end up with the following result. So this is the final result. Critical points. We are going to have one more critical point than before. We had the critical point 0, we have one critical point before in the middle, and now we have one on the axis, on the vertical axis. So, and the saddle that we had before is still a saddle. The center becomes a sink in this case, and the new critical point is a saddle. If we put all this information together, this is what we end up at the end of the day, after doing very long calculations. The saddle is the same as before. Let's put the two pictures together. That's why I repeat that picture there. The saddle is the same, but now there is a new critical point that we didn't have here. That is a saddle point, and the oscillation that they were oscillation forever in the center now become a spiral. So, for example, these are oscillation that goes towards the critical point. Before they stay at finite distance forever. Now this oscillation goes toward the critical point. Again, this is the predator and the other is the prey. Notice that when this coefficient 6, if we take 6 and we make it bigger and bigger and bigger and we go to infinity with this coefficient, infinity carrying capacity, which means infinity food, this critical point is going to go higher, and we are going to recover this picture on the axis, and then the spiral is going to be closer and closer to closed curves, to centers. So in the limit, when the food goes to infinity, these pictures will recover this picture here. So everything is consistent. And if we see the projections of the oscillations, the population of predator and prey still oscillates back and forth. But recall the population is going towards the center. So the oscillations slow down in amplitude. So the amplitude gets smaller and smaller. The oscillations stay forever, but the amplitude goes to 0, and then we are reaching at time t equal infinity the critical point that has here a population of 1 for the predator and 3 for the prey. So these are oscillations that they go to the value 3 for the prey and value 1 in this case for the predator. And that's it. That's essentially what we wanted to mention in this video. What happens in the case of finite food resources. I add here in the rest of in the next 2 pages the calculations for you, so you can do the calculations and then compare. So how we obtain this picture? Well, in the same way we obtained the previous picture for infinite food resources. So we wrote the equations, then we define what is the vector field. Now the vector field has this term here. The numbers that we are using are different from the previous example, so we need to redo all the calculations, but that's fine. Then we find the critical points. Again, the critical point is make these two equations equal 0, because recall the critical points are the points where the field vanishes. So we are solving for this equation. And well, it's more complicated now, but you can find 2 solutions pretty easy. Then there is a new third solution that you can find, and that gives us our 3 critical points we mentioned before. And then they look more or less like this: 1 critical point inside and 2 on the axis. Then we find the derivative matrix. It's a little bit more complicated because we had this extra term here. And then we evaluate at the linearizations, and we obtain, as before, a saddle at 0, 0. Then the new critical point on the axis you evaluate the derivative matrix, you do the same calculation we did before, you end up with a saddle node in this case, and you need eigenvectors just to see that this direction is important later on to do the picture. That direction is going to be that direction here in the picture, so it's important to have it. So that eigenvector is important. Then we go to the third critical point. We find the derivative matrix. Now the calculations are way more complicated, and we end up with eigenvalues that they are complex valued with a negative real part, so sinc spiral. And you have to compute the eigenvector, which is more complicated, to find how oval is the spiral, and then you end up with this picture. So I leave the calculations here, so you can use it. Let's put it here. You can use it as a guide when you do your own calculations. Alright guys, that's all for this video. See you guys in the next video.